Friends, this is Dr. Suhas Sabnis continuing my lecture series on crystallography. Today I am going to discuss some of the crystal structures that are there for your syllabus, and first of that is the diamond structure. Now, why diamond structure? Generally, in the primary stage, every crystallographer is made to go through certain important structures in his introduction to the course of crystallography, and the first of that structure is diamond structure. The question is, why do we study this structure? The answer to this is, diamond is a near ideal structure. Now, what is the meaning of near ideal structure? All the books, all the reference books, if you just see related to crystallography, say that no crystal is 100% ideal. So, concept of 100% ideal crystal, wherein there is no deformity, there is no dislocation, there is no shifting of planes, okay, or point dislocations, plane dislocations, surface dislocations, volume dislocations, or aberrations of any other kind. So these are the primary reasons why we say that crystals cannot become ideal crystals. Rarely you find that everything is fine with the crystal, and we call that crystal to be an ideal crystal. But if something is very close to it, we will call that as near ideal structure. So you will find diamond in that sense a near ideal structure, a structure which is having generally no deformity inside it, no point dislocations inside it, no structural deformities existing inside it, very closely organized structure, very neatly organized structures, I can say, and still an open structure. Diamond is not a closed packed structure, it's an open structure. Associations are open associations over there, but there is very, the way the structure is being arranged, it is so densely and so organized that we can make one claim that this structure is a near ideal structure. Second important point why we want to study diamond structure is because diamond has got variety of applications. Okay, the popular ornamental applications always stand because of its unique transmission and reflection properties. If you find a structure to be an unaberrated structure and it has very specific reflection property, throughout the structure you find unique reflection, throughout the structure you find unique transmission property, then we call that a unique property, because generally in any other case we need to derive this property by so many calibrations. That is why we study thin films. It is because we know that surfaces are aberrated, and in order to have ideal conclusions of reflection, this aberration needs to be removed. And how we can remove this? By making the films thin. Okay, and in that way we derive this unique reflection and transmission properties. But this is naturally available with diamond, that makes it a crystal which is near ideal crystal. So, and then popular industrial uses are also there. Diamond is the hardest of the hard structure. So if you have any calibration of standards of minimum hardness to the optimum hardness level, we can say, then at the top of the chart you will find the name of the diamond structure. Hardest of the hard structure. If you take a thick slab of glass also, that thick slab of glass can be cut into whatever desired shape you want it to by use of diamond cutters. Diamond drillings are there. So you can have bits of diamonds and you can drill very hard surfaces. So industrially we can use them for cutting, drilling exercises for very hard and very such surfaces in which your normal drills, normal bits do not work. So it is hardest of the hard. So industrial use is also there. Now ceramically produced diamonds is one of the most popular things. American diamonds, ornamental use, popular use. No one, generally we will go for real diamonds, but at times if we cannot, afford to have real diamonds, then we can go for American diamonds. These are ceramically grown diamonds. In the same way, ceramically grown diamonds are being also used with their unique hardness properties in the case of industries as option for cutting, welding and drilling. Not welding, cutting and drilling. So in that sense, this structure has so many ideal properties in it which I need to study. It is just like if I come to your home, you will always introduce me with the person who has got highest number of accomplishments with him. You will say that meet this person first and the rest will follow. In the same way, you go to the carbon family will get you introduced with the most ideal structure of its own family, and that ideal structure of the carbon family is diamond. Okay. So I have got a structure of diamond here to just show and explain. Before that, I want to go to the definition of this diamond structure. I will give you a very practical definition. Theoretical definitions are so many which are available in the reference books and textbooks. I will give you such a definition which will be of use to you. Diamond is derived as 2 FCC lattice being translated into one another, one being translated into the body diagonal of the other at a distance equal to 1/4 of the body diagonal with reference to the origin of the considered first. This is primary definition of any diamond structure. How do we derive it? We need to take 2 FCC lattice structures. Now if you take 2 FCC, say I have got one another structure, this is not a FCC, let us consider these two as FCC structures. Then how do we translate it? Do I translate it like this, corner to corner, face center to face center? I cannot translate it like this, and if I translate it like this, I will not derive this structure. The translation has to be a diagonal translation. Keep that in mind. How do we translate diagonally? It is just like I take it in this way and translate it. What is the conclusion? Why do we want to have a diagonal translation? It is because my diamond structure, which is a FCC structure, the parent structure, the first FCC, should not be dislocated. The corner of the first should remain the corner of the first. It should not be dislocated. The face center of the parent should remain the face center of the parent, the first. So apart from that, if there are any rest places remaining, in that rest places only I should translate my diamond, the second FCC. The second FCC is translated at the positions which are not assumed by the first FCC. Now which are the positions assumed by the first FCC? Corner is assumed, face center is assumed. Now which are the places which are remaining then? The remaining places are body center, number 1, and these 1/4 body diagonal positions. Okay, the first option is body center. Can this be translated, the second FCC being translated into the first as body center? We cannot. It is because diamond is also a FCC structure. So if you are translating the second FCC into the first, necessarily the translation cannot take this position assumed. It does mean that one more option is gone. What are more options remaining? The only options that are remaining are 1/4 body diagonal positions. And how many these 1/4 body diagonal positions are available? Just see here. So there are, suppose this structure is there. I draw this structure for you. So if body center is not allowed, face center is not allowed, what are the positions? These 1/4 body diagonal positions are the only positions in which this translation can be carried out. Now how many such 1/4 body diagonal positions are available in a cube? See, there are 8 corners. So with every corner there is one body diagonal position. So 1, 2, 3, 4 positions in the top, and there are 4 positions in the bottom, 1, 2, 3 and 4. So 8 positions are allowed here. So 8 positions are there which are called 1/4 body diagonal positions, in which the second FCC can be translated into the first. So if I am carrying out this translation, how many number of atoms are there in a FCC to translate? Because I cannot translate fractionally. Fractional translation is not allowed. So in total, in any FCC, there are 4 number of atoms per unit cell. So if I am translating the second FCC into the first FCC, the logic says to me that I am translating 4 atoms of the second into the first. And there are now, as I have told, 8 positions available. 4 in the top plane, 4 in the bottom plane. And to fit, I have only 4 atoms here. Second FCC has only 4 atoms. So getting my problem here? My problem says here that I have 4 atoms to translate and I have 8 positions to assume. Will you say now that I will fractionally divide half into all 8 positions which are 1/4 body diagonal? Of course we cannot. It is because half positions cannot be inside the body. Inside the body we need to have complete atoms. So symmetry laws will play a rule. So if there are 4 positions, 8 positions and 4 atoms, 2 will be in the top plane and 2 will be in the bottom plane. Getting my point? So 2 in the top plane, 2 in the bottom plane, that too in a way following the laws of symmetry. Symmetry laws need to be followed. Keep that in mind. What are the symmetry laws? The symmetry law says that if, and the density calculations will also be have to be sufficed over there. So naturally if you are filling 2 in the top, so where we are filling the 2 from the top, from the same bottom side, places need to be vacant. Getting my point? So if I am having 2 positions here, if you just see being filled in the top plane, the same translation at the bottom will give me vacant places. The same way at the bottom, if I say there are 2 positions that I have filled over here and here, if you just see it here, more focus if you can show, this is 1 and this is second, and then if you are just translated the same positions on the top positions are vacant. This is law of symmetry. The law of symmetry says that the positions which are filled from the top should be vacant from the bottom, and the positions which are filled from the bottom should be vacant at the top. That gives me sufficing answer to the laws of symmetry, in which the second FCC can be translated into the first. Again coming back to the definition, to say that 2 FCC lattice being superimposed over one another, one being translated along the body diagonal of the other, at a position equal to 1/4 of the body diagonal. Now where is this position of 1/4 of the body diagonal? These are these positions. So this is corner and this is 1/4 body diagonal. What is the meaning of 1/4 body diagonal? It does mean that if I am taking the calculation, the distance from this position to this position, the entire distance is, suppose this distance is the body diagonal distance, 1/4 of this distance will be the distance between this corner and the center of this particular translated atom. Okay, so this is the definition of 1/4 body diagonal position, 2 on the top side, 2 on the bottom side, sufficing the laws of symmetry. Now, concluding further, for this particular diamond structure now, as I have defined, I need to find 4 parametric calculations. The first parametric calculation is coordination number. If you just see here inside the structure, every atom which is completely inside the diamond structure, this 1/4 body diagonal position, of course, assumes itself to be a center of tetrahedron. You know the tetrahedron? One top, 3 points at the bottom forms a tetrahedron. Okay, so there is, if you just see, it assumes itself to be a center of tetrahedron being formed by 3 face centers and 1 corner. 3 face centers and 1 corner. 3 face centers at the base and 1 corner at the top. And the translated atom assumes itself to be the center of this formed tetrahedron. You will not see that tetrahedron, but it is actually that arrangement of bonding pattern we say. Okay, so this tetrahedral bonding pattern is unique characterization of any carbon structure as such. So naturally, you will find here the same repeated. Every atom which is completely a part of this structure assumes itself to be a center of tetrahedron being surrounded by 4 another atoms which belong to neighboring unit cells. So all of these are contributing. Every face center is contributing to the neighboring unit cell. Every top, every corner we say, it also contributes to the neighboring unit cell. So naturally, my coordination number is 1, 2, 3 and 4. The second parametric calculation to be done is number of atoms per unit cell. Number of atoms per unit cell. Now it's all analytical calculation here. We know the law for this. The law for this says that NC by 8 plus NB by 1 plus NF by 2, where NC is nothing but number of atoms which are corner atoms, NB number of atoms which are body centered or body center like atoms, and NF which is number of face center atoms. So naturally, how many number of corners are here? 8 corners. So 8 by 8. How many number of body centers? There are no body centers here, but there are body center like atoms. How many are translated like that? 1, 2, 3 and 4. 2 at the top, 2 at the bottom. So it is 4 by 1 plus how many face centers? Of course, there are 6 faces to the cube, so 6 face centers. So 6 by 2. It is 1 plus 4 plus this is 3. It is 8. So number of atoms per unit cell for the diamond structure is 8. The third parametric calculation to be made is the atomic radius of the diamond structure. Let us calculate for that. The atomic radius is calculated in this way. See, you need to see the diagonal view here. There is one atom in the corner, there is 1/4 body diagonal position, and there is one atom in this corner, and the rest of the place is vacant. The question is, if there is no atom present, should I calculate or should I not calculate the distance as well? Of course, I need to calculate the distance. So by symmetry laws, I need to assume certain positions. So if there is one real position, I assume 1/4 body diagonal position, which is an assumed position, which is not a real position. Then also one body center position is remaining. So I draw one more assumed body diagonal position. So if I join this, I get this distance. Out of this distance will be 2. This distance will be r, radius of the atom. This distance will be 2r. This distance will be 2r. This distance will be 2r, and this distance will be r. So the entire distance, if we calculate, this entire distance will be equal to r plus r is 2r, plus 2r 4r, plus 2r 6r, plus 2r 8r. So this is 8r. Now calculate this distance. Now this distance of course is equal to A, which is lattice parameter, and the last distance is this distance, which is equal to the face diagonal, which is nothing but A root 2. So rationally calculated, I get one diagram over here for simplification, which is 8R A root 2 and 190 degrees. So I get a right angle triangle. Solve this right angle triangle, I get 8R square is equal to A square plus A root 2 square. Getting my point? By simple calculations we can always do that. It is nothing but 64R square will be equal to A square plus 2A square. So 64R square is equal to 3A square. So R square will be equal to 3 by 64 A square. So what will be R? R will be root 3 by 8 A. This is my atomic radius. And final calculation needs to be made for atomic packing factor. This atomic packing factor, I will show you how to calculate it. Have you written down this? So this is for the atomic radius, and the last calculation I am going to make for the atomic packing factor. The atomic packing factor is defined as, we call it as APF, atomic packing factor. It is nothing but, we have defined this, we already know, 4 by 3 pi r cube into n divided by a cube. Okay. Now 4 by 3 here, pi, what is r here? Atomic radius, we have just calculated it. It is root 3 by 8a cube of this into n. N means number of atoms per unit cell. We have calculated it for the diamond structure. It is again 8 and divided by a cube. So solve this. 4 by 3 pi, this is 3 root 3 by 8 into 8 into 8. Okay, this is a cube into 8 upon a cube. Okay, now just see here, a cube and a cube gets cancelled. One of the 8 and 8 gets cancelled. Okay, now this is 4 and this is 2. 3 and 3 will get cancelled. So I get pi root 3 upon this 8 into 2 is 16. Logically you need to put the value of pi, and if you put the value of pi against this, you get 0.34. This is atomic packing factor. It does mean atomic packing efficiency is nothing but atomic packing factor into 100, which is nothing but 0.34 into 100, which is 34%. So if 34% is something we see, that is the reason of hardness inside the structure. 2 FCCs are translated into 1. What is the packing efficiency of any FCC? It is 74%. So 2 structures which are having 74% and 74% packing efficiency are added into one another. Naturally, I will conclude that the formed structure will have more density or more packing than 74%. But what I am getting? I am just getting 0.34 or 34%. It does mean that it is more ordered packing. It's a definitely something which is, I can explain it as, there are 2 rooms suppose, and I have a lot of furniture and so many other things inside that. I pack that into one, but also make one arrangement that the 2 rooms and whatever furniture is there arranged in one also gives me a space which is more than which can be available in any one single room. So that is the nature of the order that we can assume in diamond, and that gives the reason of hardness associated with the structure. 34% is the packing, so 100 minus 34, it is 66% space is not occupied, it's a void space, reason of openness. That's where I said in my discussion that the structure is an open structure. So calculation of coordination number of atoms per unit cell atomic radius, and finally atomic packing efficiency concludes the entire discussion on diamond structure. I hope you understood this. Thank you.